Hello, Chem 1132. This is Mr. Coker, and I'm recording the lecture because class was canceled on February 17th because of the icy weather. So we have been discussing buffers. By the way, before I get started, the lab that was going to be on Thursday will be on Tuesday. So chapter 14, my plan is to finish all the slides for chapter 14. We will not make up the quiz. The quiz was attached to the announcement. So the quiz is actually open resources, whatever resources you want to use. But so I'm not expecting you to just do it without looking anything up. Just consider it sort of like a homework. You can use your resources, and except I'm going to put it in the quiz section. So just consider it an open note quiz. To turn in the quiz, simply email me a copy of your answers, 1 through 10. Just say 1A, 2B, 3C, 4D, whatever, and get me your answers to the quiz that way. Okay, so back to the notes that we would have covered on Thursday, and I'm also doing one section that I was going to cover on Tuesday because we have to find time for that lab. So finishing chapter 14, which is about 68 more slides, I believe. All right, so we've been, just to put us in context of where we are, we've been talking about buffers. And buffers are mixtures of weak acids and conjugate bases, or weak bases and their conjugate acids. And when you have a mixture of those two things, the pH will tend to hover or remain near a particular value for that particular mixture. You can make buffers that buffer around pH 10 and keep the pH around 10. You can make a buffer that'll buffer around 3 and keep the pH around 3. Depending on which weak acid and which conjugate base combination you have, the pH will be centered around a particular value. The idea of a buffer is the way that it holds the pH constant is that the weak acid is going to be available to neutralize any base that might be added, and the conjugate base is available to neutralize any acid that might be added. You can work out buffer problems by setting up an ice table. We know those can be a bit cumbersome though. One nice thing about the way the ice table always works out is that you can simplify the results of the ice table down to this equation called the Henderson-Hasselbalch equation. And Henderson-Hasselbalch is a equation that should be used only with buffers. Do not try to use this with a pure weak acid or a pure weak base problem. This is only when you have appreciable amounts of your weak acid and conjugate base, or weak base and conjugate acid. Now, this particular form of the Henderson-Hasselbalch is set up for a weak acid HA and its conjugate base A minus. So this could be acetic acid and A could be acetate. It could be nitrous acid and A could be nitrite. A minus would be NO2 minus, and HNO2 would be your acid. But any weak acid and its conjugate base, where you've got a decent amount of both. In fact, the best buffers are when you have approximately equal amounts or equal amounts of HA and A minus, but you don't have to have that exactly equal. The pH is going to be centered around pKa. So in other words, your pH is going to be about right where the negative log of Ka centers. So if you've got a Ka of 1 times 10 to the minus 4, your buffer, so that's the Ka of your weak acid HA. If your Ka of the weak acid HA is 1 times 10 to the minus 4, your buffer is going to be centered at its pH around 4, because the negative log of 1 times 10 to the minus 4 is 4. However, if you if you change the ratio of your conjugate base to weak acid, then your pH is going to shift either up or down from that value. If your ratio of A minus and HA is 1, so in other words, if the conjugate acid, if the acid and its conjugate base have an equal concentration, you have 1 molar HA and 1 molar A minus, or 2 molar HA and 2 molar A minus, then the ratio A minus, or base to acid, A minus to HA, is going to be 1, and the log of 1 is 0, so the pH then simplifies to just equal pKa. However, if your conjugate base and weak acid ratio is not 1, then there will be a slight change to that pH, but it's always slight. It's up 0.1, down 0.1, something like that. So what will happen, even if you start with a 1-to-1 ratio, if you did happen to add strong acid or strong base, it would change that ratio. For example, let's say you have equal amounts of A minus and HA, and you add some H plus, you add some strong acid. The H plus is going to react with the A minus, meaning we're going to get rid of that H plus. But that H plus reacting with A minus is going to generate HA, and it's going to use up A minus. And so the ratio of A minus to HA is going to go down because A minus is going to be less and HA is going to be more. And so you're no longer taking plus the log of 1, now you're taking plus the log of something less than 1. So then that's negative, and you're going to subtract from your pKa, and your pH is going to be lower. So the addition of acid will still lower pH, but not nearly as much as it would if the buffer were not present. Okay, so that's my summary of buffers. Buffers are weak acids and conjugate bases that can help to moderate the pH and keep it around the value pKa, or negative log of the Ka of the weak acid. Of course, all of what I say about this is a weak acid conjugate base. You can also use the same language to discuss a weak base and its conjugate acid. All right, so we're finding the pH of 0.75 molar. I think we did this Tuesday night. Lactic acid and 0.25 molar sodium lactate with a Ka of 1.4 times 10 minus 4. The Na plus is not going to be anything. It's going to be the weak acid and the conjugate base lactate. So lactic acid, HC3H5O3, lactate, C3H5O3 minus. Those are your important species. And so Ka, H plus times lactate over weak acid should equal 1.4 times 10 minus 4. Since there's very little shift in this equilibrium, the minus x and plus x's are going to be negligible. We can assume then that the lactic acid is going to be at 0.75 molar and the lactate at 0.25 molar. So your H plus, using the Ka equation and rearranging things, and solving for H plus, you're going to get 4.2 times 10 minus 4, which gives you a pH of 3.38. Now, more quickly, you could just plug into the Henderson-Hasselbalch. pKa, the negative log of 4.2 times 10 minus 1.4 times 10 minus 4 is your Ka. 1.4 times 10 minus 4. The negative log of 1.4 times 10 minus 4 is 3.85. Then we add the log of the ratio of the base to the acid, 0.25 over 0.75. Now we get the log of 1/3. And when you take 3.85 and add the log of 1/3, you get 3.38. So that's the same answer with the Henderson-Hasselbalch as you would get by solving the Ka equation. And I think the Henderson-Hasselbalch is a little quicker. Okay, so we've got a buffered solution with a 0.25 molar ammonia and 0.40 molar ammonium chloride. So note here the chloride's not going to be important, but the ammonium, NH4 plus, is going to be the conjugate acid of the weak base ammonia. So this is in fact a buffer. It is a weak base and its conjugate acid, ammonia and ammonium. Now we're given a Kb value. So we could solve the problem using, the ice table and approach and all that. And assuming the shift is to the right, minus x and plus x and plus x, and solve for the x's and get the OH minus that way. And we get a pH of 9.05. So 9.05 would be your pH. Now, something they didn't do is they could have used the Henderson-Hasselbalch. Let's back up and talk about how we would have used the Henderson-Hasselbalch on this one. We have the molarity of the base, 0.25. We have the molarity of the weak acid, 0.40. We have the Kb. Now remember, Henderson-Hasselbalch needs pKa, but we know that Kb times Ka equals 10 to the minus 14. So if the Kb is 1.8 times 10 minus 5, I believe that works out without having a calculator with me right now. I believe that works out to 5.6 times 10 to the minus 10. And then when you do that would be the Ka value. So what you could do here is you could solve for the negative log of 5.6 times 10 to the minus 10 plus the log of 0.25 over 0.4. And in that case, you would still get this 9.05 number that you got by analyzing it with an ice table. So ice table works. If you like ice tables, you're comfortable with ice tables, fine. However, if it's a true buffer, meaning a good, strong mixture of a weak acid and its conjugate base, you can also use this Henderson-Hasselbalch equation to get the pH. Buffers need to contain large concentrations of the weak acid and the conjugate base. If they only contain very small amounts, they're not going to be able to withstand very much addition of H plus or OH minus. Our goal is to keep this ratio of acid to base, base to acid here in the Henderson-Hasselbalch. We want to keep that ratio as close to 1 as possible. If those numbers start out as small molarities, then addition of acid or base is going to have a big effect on this ratio, which is going to change your pH a lot. But if these molarities are close to 1, are very large values, and their ratio is close to 1, the ratio is going to stay close to 1, even though you're adding strong acid or base to the solution. Oh, by the way, adding water to the solution, let's go back to our Henderson-Hasselbalch, sorry. Adding water to the solution actually has no effect on the pH, because the change in the molarity of the base and the change in the molarity of the acid is the same. Let's say you double the volume of a buffer. The base concentration is going to cut in half, and the acid concentration is going to cut in half. And if you cut the numerator and the denominator both in half, the ratio stays the same. And so, interestingly, diluting a buffer does not change its pH. Sorry about all this flipping around through slides here, but I wanted to go back and talk about the Henderson-Hasselbalch equation a little bit. Okay, so buffers need to have large concentrations of the weak acid and the corresponding weak base. You can have weak acid HA and conjugate base A minus, or weak base B like ammonia and conjugate acid BH plus like NH4 plus, ammonium. If you add H plus to the buffer, it's going to convert your weak base to the conjugate acid form. So it's either going to convert A minus to HA or B to BH plus. Now that conversion is going to change that ratio of base to acid. It's going to lower the concentration of the base and increase the concentration of the acid. And that will have an effect on the pH. It's just going to be lessened by the nature of how a buffer works. If you add OH minus to a buffer, it converts the weak acid form to its conjugate base. So HA converts to A minus. That's going to raise that ratio of A minus to HA, which is going to then increase your pH slightly. So the pH of the buffer is determined by that ratio. So as long as we keep that ratio about the same number, in other words, don't let that ratio change very much, the pH will be holding in real close at that pH equal pKa value. So if you keep your concentration of buffering materials, HA and A minus or B and BH plus large compared to the amount of H plus and OH minus you add, then you're going to be ready for to keep the pH close to pKa. So that would be what we call buffering capacity. How many protons, H plus, or hydroxide ions can your buffer absorb without any significant change in its pH? So the pH of a buffered solution is determined by the ratio of A minus to HA. Buffers that have large capacity are going to have large concentrations of H minus or A minus and HA. And because of that, the A minus can absorb a lot of protons, or the HA can absorb a lot of hydroxide ions. And we'll see very little change in that ratio, and so the pH will remain relatively constant. So let's look at two different buffers. One is 5 molar acetic acid and 5 molar sodium acetate, acetate being the conjugate base of acetic acid, and then 0.05 molar, 1/100th the molarity, acetic acid and sodium acetate. And in each case, we're going to see what will happen to the pH when 0.01 moles of HCl is added. We're going to add it in the gaseous form so as not to change the volume of the solution. Remember, acetic acid has a Ka of 1.8 times 10 minus 5th. So the Henderson-Hasselbalch equation will say pH equals pKa plus log of acetate concentration over acetic acid concentration. Now in both A and B, the molarity of acetic acid and the molarity of acetate are equal, 5 and 5 and 0.05 and 0.05. And so we're looking at the log of a ratio where the top and bottom are equal. When the top and bottom of a ratio are equal, it's 1. And so the log of 1 is 0. So in both cases, A and B, your beginning pH is pKa, or negative log of 1.8 times 10 minus 5th, which is 4.74. So the acetic acid acetate buffer centers its pH around 4.74, which is the pH anytime the molarity of the acetate and the acetic acid are equal. However, adding HCl to these two solutions is going to change the amount of acetate and acetic acid. See, the H plus from the HCl is going to react with the acetate, which is going to lower the amount of acetate, which is going to, and also raise the amount of acetic acid, because the reaction is going to be H plus from the HCl plus acetate is going to make acetic acid. So we're going to use up acetate and make acetic acid. Now, because this is acetic acid is a weak acid and acetate is a better base than water, we're going to assume that the added H plus converts acetate to acetic acid in a stoichiometry way, not in any kind of equilibrium way. In other words, we're going to assume the reaction goes to completion. So our reaction H plus plus acetate yields acetic acid is going to be 0.01 moles of H plus is going to react for solution A with 5 moles of acetate, which is going to bring our, there's a misprint here, the acetic acid, I'm sorry, not a misprint, which is going to bring our acetate down to 4.99 moles, and our acetic acid is going to be raised to 5.01 moles. Now 4.99 and 5.01 are both still fairly close to 5, And so in the Henderson-Hasselbalch equation, when you plug those numbers in, you're going to still have a ratio very close to 1. In fact, the log of 4.99 over 5.01 is 0.0017, which is actually not going to even change based on the sig figs rules. It's not going to even change your value in the second sig fig. 4.74 is still going to be 4.74. Slightly less than 4.74, but not enough to be called 4.73. However, in the case of the part B, because the A minus and HA start at 0.05, 0.01 is going to be a difference in that ratio. See, 0.05 and 0.05 was your original amount for part B, and after the reaction, your A minus is now down to 0.04 because 0.01 moles of H plus reacted with it, and your HA is up to 0.06. So now we're looking at a ratio of 2/3 for your base to acid. So here it is worked out, kind of like an ice table, not exactly because it's not an equilibrium problem, it's a stoichiometry problem, but 0.01 moles of H plus and 0.05 moles of acetate is going to make 0.04 moles of acetate and 0.06 moles of acetic acid. And so now your ratio is no longer 1, so you don't have the log of 1, but your ratio is now the log of 0.04 over 0.06, or log of 2/3. And the log of 2/3 is negative 0.18. And so now your pH has dropped 0.18 from 4.74 to 4.56. So with the large capacity buffer, 5 molar and 5 molar, we saw virtually no change in the pH. With this lower capacity buffer of only 0.05 molar acetic acid and 0.05 molar acetate, we see a change of almost 0.2 pH units. So your optimal buffering, in other words, the best buffering you can get, is when your HA and your A minus concentrations are equal, and when you have fairly high concentrations of HA and A minus, which will keep that ratio close to 1 as you add H plus or OH minus to the buffered solution. So if you are trying to pick a weak acid, in order to choose the proper weak acid to make a certain pH. So let's say that I wanted a buffer that has a pH of 3. What I should search for in the list of weak acids is a weak acid with a pKa of 3. Or in other words, a weak acid with a Ka of 10 to the minus 3. So then if I pick a weak acid with a Ka of 10 to the minus 3, then my pH will be 3 as long as my A minus to HA ratio is 1. So choosing a buffer, choosing a weak acid to be used as a buffer, is you want the pKa of the weak acid to be as close as possible to the pH you're trying to generate. Now it doesn't mean you have to get it right on the button. You can alter the ratio of A minus to HA a little bit to get your buffer to the pH you actually want it to be. So let's say we had these 4 possible weak acids and a chemist was trying to figure out which one to choose to get a buffer of pH 4.30. So 4.30, if we look at the anti-log of 4.30, it's 5 times 10 to the minus 5th. So the closest thing we have here to 5 times 10 to the minus 5th is actually benzoic acid, which is 6.4 times 10 to the minus 5th. So the benzoic acid would allow us to have an HA minus ratio of 0.78. So then that would be the best choice. Otherwise, we would have to have a ratio of like 4 to 1 for propanoic acid or 3.7 times 10 minus 2 for chloroacetic. See, our best buffer is when the ratio of A minus and HA is close to 1, and that would be for the benzoic acid. So benzoic acid is our choice, even though the optimal buffering pH for benzoic acid would be 4.19. It would still be a reasonable buffer with a approximate HA to A minus ratio of 1 if you altered its pH to 4.30. So these are the homeworks for this week. And I'm going to go ahead on into 14.4, titrations and pH curves. So if one were to measure pH at different points during a titration, we would be creating a titration curve or a pH curve. So just to remind ourselves, titrations are used to determine how much acid or base you have in a solution, to determine its unknown concentration. We call the solution we add that we know the concentration of, we call it the titrant, and then we titrate it with a burette into the unknown solution, or the titrand. And we want to stop when the unknown is completely used up, but no further than that. And so we want to stop at the equivalence or the stoichiometric point. Now, ideally, we want that stoichiometric point to correspond with the change in the color of an indicator. Remember with the phenolphthalein, when it changes to faint pink. Now, the change in the color of the indicator is actually called the endpoint. So if we choose the indicator properly and we titrate carefully, our endpoint, which is the change in the color of the indicator, where we stop adding the known concentration titrant, that endpoint will correspond to the stoichiometric point, and we can do stoichiometry to figure out the molarity of the unknown or the titrand. A pH curve can be used to analyze and help us understand what's happening as acid is added to base or base is added to acid. Sometimes on pH curves, instead of using moles, they may use millimoles. A millimole is simply a thousandth of a mole, just like a milliliter is a thousandth of a liter. And so, for instance, if 1 liter contains 1 mole, you have a 1 molar solution. If I have some 1 molar acid and I add 1 milliliter of it, that's 1 millimole of the acid being added. So just keep in mind that molarity is moles per liter, but it's also millimoles per milliliter. So since we typically add milliliters, we can think of it as adding millimoles or thousandths of a mole of acid or base to each other. Okay, so here's a typical pH curve. It is not a straight line graph, and that's due to the log basis for the calculation of pH. Since pH is based on logs, let's say you're starting with a strong acid here, like nitric. If your nitric acid is 0.2 molar, then your pH is actually going to be slightly below 1. But to get to a pH that's 1 unit higher, you have to neutralize 90% of that strong acid. And so your pH actually is going to be fairly level until you get very close to your equivalence point. So the way it actually works with a strong acid is the first rise in pH of 1 unit is after 90%. You have to decrease the molarity of H plus 90%. To get to the next pH unit, it has to be 99%. To the next pH unit, 99.9. To the next pH unit, 99.99. And so we see that it's the pH is fairly constant for a long time until it begins to rise much more quickly as you get closer and closer to the equivalence point. The equivalence point would be when you had equal moles of strong acid and strong base, which should give you a pH of 7. And so your pH goes along rising very slowly, and then it gets closer and closer to the equivalence point, and it shoots up very quickly and goes right through that 7. If you've had a high enough level math, you would know that the equivalence point on this graph corresponds to what's called an inflection point. It's an inflection point because the left side is concave up and the right side is concave down. And so we have this inflection point at the equivalence point. So on a titration curve, you can always recognize that equivalence point. In other words, when you've added equal amounts of acid and base to each other, you can recognize that equivalence point by the center of that S, because these pH curves look like S's. And the very center of that S is where you've added exactly the right amount of acid and base, and you should stop adding and do your calculations. Now, this particular graph goes beyond the equivalence point and shows you what will happen to the pH as you keep going. And in fact, what this one does is it gets higher and higher and gets closer and closer to 13. 13 would be the pH of 0.1 molar NaOH. And so after neutralizing all the acid, then the base begins to pull the pH up to the value of closer and closer to the pure base pH. So before the equivalence point, H plus and pH can be calculated by dividing how many moles of H plus you have, dividing by the liters of the total volume. Now it'll be the total volume because the addition of the base does add volume. So adding the base to the acid changes the milliliters of the acid, and so it increases it. So your moles of remaining H plus, because you can assume that every mole or millimole of OH minus is going to neutralize a mole or a millimole of H plus. So it's actually stoichiometry. The H plus and the OH minus reaction goes to completion. There is no equilibrium to calculate. So when you have added exactly equal amounts of OH minus and H plus, then you have a neutral solution with a pH of 7. After the equivalence point, your OH minus that you're adding can be divided by the total volume to get your POH, and from that calculate your pH. This is actually the reverse of the pH curve. This would be what would happen if you started with a base and then titrated it with an acid. So you'd just get the opposite effect. You would start with your pH high. As you got closer and closer to the equivalence point, it would shoot downward, and then it would level off. Now, hopefully these curves show you why you get such a dramatic color change for your indicator phenolphthalein when you get to that equivalence point. It goes from colorless to usually a fairly dark pink with just the addition of one drop. See, that's because that drop causes you to blow through that equivalence point, and the pH rises sharply when you get right around that equivalence point. So it's actually very difficult to get a faint pink, because a faint pink means that you've hit that equivalence point right on the button. So that's, just a drop or two, and your pH changes dramatically when you are in and around that equivalence point. And so your color change can happen quickly. So for a strong acid, strong base, everything's stoichiometry because everything happens completely. For a weak acid where you're adding a strong base, you actually have two steps. The addition of the strong base to the weak acid will neutralize the weak acid and generate the conjugate base. But once you've done that, you then have to work out an ice table problem or possibly a Henderson-Hasselbalch question or equation to calculate your pH. if you were trying to calculate the pH you would have with the addition of a certain amount of strong base to a weak acid, you would convert the weak acid to its conjugate base, but then do the math on what you have then with your weak acid and conjugate base to see what the equilibrium tells you would be your pH. Okay, so let's say we have a weak acid, HCN. It's dissolved in water. It's really weak, Ka 6.2 times 10 minus 10. We have a 50 milliliter sample with 0.1 molar. And then we're titrating it with 0.1 molar NaOH. They've got us calculating the pH after 8 milliliters of the 1 molar NaOH has been added, at halfway to the equivalence point, and then at the equivalence point. Now, they could have had us calculate the pH before any NaOH was added, in which case we would have just done an ice table problem with the 50 milliliter sample of 0.1 molar HCN. But for the 8 milliliters added, remember 50 milliliters of 0.1 molar would be 5 millimoles. 8 milliliters of 0.1 molar would be 0.8 millimoles of strong base. So we have 5 millimoles of HCN and 0.8 millimoles of OH minus. So considering this to be stoichiometry, the 0.8 millimoles of OH minus will be completely used up, brought down to 0. And 5 minus 0.8 means we'll be down to 4.2 millimoles for the HCN. The CN minus, however, started at 0, but the OH minus reacting to the HCN made CN minus, so it's up to 0.8 millimoles. So when we do our ice table on this, we'll be calculating the molarity of the HCN and the CN minus from the millimoles and the milliliters. Notice I'm not dividing by 50, we're dividing by 58 milliliters instead of dividing by 50. So my preference would have been that they don't show you 4.2 divided by 58, that they would have worked that out and give you a decimal on that. But the HCN is going to be minus x, the CN minus plus x. We're going to neglect the x. We're going to solve for x. We're going to get the H plus. And yada, 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 yada. Ice table, ice table, ice table. So the x, when it's all said and done, calculates out to be 3.3 times 10 to the minus 9 molar, or a pH of 8.49. So even though we have a weak acid and we haven't added enough base to neutralize it, our pH by now is actually all the way up to 8.49. We're actually in the basic part of the pH scale. Now at the halfway point, our 5 millimoles of HCN is going to be neutralized down to 2.5 millimoles of HCN because we're going to add 2.5 millimoles of OH minus, which in that case, the HCN is lowered to 2.5 millimoles, but the CN minus that you get by reacting the OH minus with the HCN is now itself up to 2.5 millimoles. And so we actually have a buffer situation where our HCN and CN minus are going to be equal. So because of the Henderson-Hasselbalch, that means the pH equals a pKa. So at the halfway point in the titration, the pH equals pKa. So when you're titrating a weak acid with a strong base, your pH will be pKa at the halfway point, 9.21. Now at the equivalence point, your pH will actually be determined by the pH of the weak base, CN minus. At the equivalence point, all 5 millimoles of HCN have reacted with 5 millimoles of OH minus to make 5 millimoles of CN minus. Now your CN minus is going to have a Kb that's equal to Kw over Ka, and a volume of 10 milliliters, or I'm sorry, 100 milliliters. Now, it was originally 50 milliliters of HCN, but you've added 50 milliliters of NaOH, so you've doubled your volume. You're now up to 100 milliliters. So you're, instead of being 0.1 molar, you're now down to 0.050 molar because of the dilution effect you get by adding the base to the acid. But you can just do a quick ice table on 0.05 molar CN minus, solve for your X, get your POH, and get your pH from that. And it comes out to 10.96 at the equivalence point. So if we were to graph it, we would start out with the pH of the pure HCN. Then we would, at 8 milliliters, we'd have the pH of 8.49. At the halfway point to 50 milliliters, so in other words, at 25 milliliters, our pH would be 9.21. At the equivalence point, 50 milliliters, our pH would be 10.96. And then later on, the pH would rise until it was approximately 13, which is the pH of the pure hydroxide, sodium hydroxide. Okay, so quick concept check. If we have a Ka of 6.2 times 10 minus 10, and we have 0.1 moles of HCN, and we add 0.04 moles of NaOH, and it's all in 1 liters, what do we have? What's our solution going to be? Well, you've got the HCN, which is more moles than the NaOH. You've got the Na plus, the OH minus, and the water. So immediately upon mixing and before any reaction occurs, you've got some HCN and some OH minus, Na plus and water. As the reaction occurs, it's going to be stoichiometry. The HCN and the OH minus are going to react until one or the other gets used up. And in this case, it would be the NaOH, the OH minus. The OH minus will get used up, and the HCN number will come down, and you'll now have HCN and CN minus. And you'd have to figure out the pH from that. Finding a pH by mixing 0.2 molar acetic acid with 0.03 molar NaOH, 0.20 moles of acetic acid, and 0.03 moles of NaOH. I would have done this one on the board. In fact, maybe on Tuesday I will do this one on the board. But you might try it yourself. So I would just encourage you, try this yourself and remind me on Tuesday to work this one out on the board. If you cannot figure out how to get a pH of 3.99. My hint would be use the Henderson-Hasselbalch equation because the NaOH will convert your acetic acid to acetate. You have 0.2 moles of acetic acid, 0.03 moles of OH minus. Your stoichiometry is going to be that your OH minus is going to go to 0. Your 0.2 moles of acetic acid is going to come down to 0.17. And your acetate, C2H3O2 minus, is going to go from 0 to 0.03. That's your stoichiometry. And then based on the molarity of the acetate and the molarity of the acetic acid, see if you don't get a pH of 3.9. 99, I'm sorry. Now, what's the pH mixing 100 milliliters of 0.1 molar acetic acid, which has a Ka of 1.8 times 10 minus fifth, with 50 milliliters of 0.1 molar NaOH? Well, 100 milliliters of 0.1 molar acid and 50 milliliters of 0.1 molar NaOH, that's actually the halfway point of the titration. You added actually half the amount of base it would take to neutralize all of the acetic acid. So half of your acetic acid has been neutralized and turned into acetate, meaning you've got half and half, you've got equal amounts of acetic acid and acetate. With equal amounts of acetic acid and conjugate base, you have a perfect buffer, and it doesn't matter what the molarities are. If it's half and half, then your pH equals pKa plus log of 1, or pH equals negative log of 1.8 times 10 minus fifth, or pH equals 4.74. So calculate the pH of the equivalence point, and I probably need to work this one out on the board because I don't have it typed in. So remind me again on Tuesday, work this one out on the board. Here at the equivalence point, you actually have acetate. So instead of the pH being 7 at the equivalence point, the pH is slightly above 7 because this becomes a weak base problem with an ice table and a Kb value. So your acetate completely converts to, your acetic acid completely converts to acetate, and so then you set up an ice table with the molarity of the acetate and find Kb and find OH minus and POH and find the pH. Okay, so this is what you would think, which you would get if you neutralize a weak base with a strong, or I'm sorry, weak acid with a strong base. Notice your pH doesn't start out down around 0. Your pH starts out, like for this acetic acid, around 3. It starts rising more rapidly, but then levels off as it begins to buffer. So at 25, your pH should equal your pKa, so because that's the halfway to the equivalence point. Then at 50, you still see that strong rise in your pH, but the center of that S-curve is not at 7. The center is above 7 because at the equivalence point, you actually have a weak base solution because the strong base converts your weak acid to a weak base. Acetic acid and NaOH make acetate, which is a weak base. And then you see your pH continue to rise, headed toward the pH of 0.1 molar NaOH. So your shapes are quite different. Your strong acid starts really low, rises really sharply, and then levels off. Your weak acid is going to start a little higher, it's going to rise more quickly, then level off, and then rise again. But the vertical part of a weak acid titration is curve is not as tall as a strong acid. So picking the right indicator, because different indicators change colors at different pHs, is much more critical with a weak acid because you have a less forgiveness because you have less vertical region to your equivalence point area. Your strong acid, you could pick anything that is anywhere close to that vertical part, and you'll probably get your color change happening at the right time. But with your weak acid, you got to choose an indicator that changes color somewhere in that vertical region, which is a much smaller window. And that window gets smaller and smaller and smaller as your Kas get larger, because remember, your Ka, your pKa is going to be your middle point halfway to the equivalence point. So as you begin to raise that, you shorten that vertical region. So notice that the Ka equals 10 to the minus 2, 25 milliliters, pH is 2. For Ka equals 10 to the minus 4, 25 milliliters, pH equals 4. So if you've got a weak acid, you want to determine its Ka. One way to do that is to create a mixture where you have half and half of the weak acid and its conjugate base. So you could take 2 millimoles and titrate with 0.05 molar NaOH, and at 20 milliliters you would have 1 millimole of solid acid and 1 millimole of conjugate base. So your pH of 6 means your Ka would be 10 to the minus 6. So 2 millimoles HA, 1 millimole of OH minus means you end up with 1 millimole of HA and 1 millimole of A minus. So because of the Henderson-Hasselbalch equation, your pH is going to be, what's this? Yeah, they've calculated, I mean, they've done a lot more work there than they need to. They've done the whole ICE table with the molarities and added the 20 and the 100 to get them liters and all that. But in the end, all this major math, they should just realize that you've got equal amounts of weak acid and conjugate base. So if your pH is 6, your Ka is 1 times 10 minus 6. So they did a lot more work than they needed to if they just realized that 1 millimole of A minus and 1 millimole of HA in the same solution means pH equals pKa. Okay, so to illustrate sort of how you would maybe try to generate a pH curve, they show here adding different volumes of HCl with 0.1 molar to different volumes or different, adding it to a certain volume of ammonia, and how much ammonia and how much ammonium you'll have and how much H plus that means you'll have, so what your pH will be. But ammonia calculated at different volumes of acid added will have a pH curve like this. And so you see this is sort of maybe a mirror image or a inverse image, inverted image of what you would look at like for a weak acid and strong base. This is a weak base with a strong acid. Notice your equivalence point is below 7. That's because when NH3 reacts with HCl, it makes NH4 plus. So at the equivalence point, you have NH4 plus. NH4 plus is actually a weak acid, so your pH is less than 7. At 25 milliliters, looks like your pH is right around 9. And so what that gives you is the Ka of ammonium, from which you could find the Kb of ammonia. Okay, and wrapping it up here with one more section, 14.5, acid-base indicators. You can use a pH to monitor your pH meter to monitor your pH while you're making a titration, and then simply take a curve and find that vertical region and solve for the pH at that point, and say, okay, that's where I've added the right amount of base to neutralize my acid. Or, like we do in class, we can add an acid-base indicator that changes color. However, you have to be careful to choose your acid-base indicator so it changes color at the proper pH. Phenolphthalein, the reason why phenolphthalein works as an acid-base indicator, and this is a pretty critical point here, because how in fact do indicators know what the pH is, and how can they change color at different pHs? Indicators, this is the secret, indicators are weak acid and conjugate bases. The colorless form of phenolphthalein is the weak acid. The pink form is its conjugate base. When it's got the H plus on it, it's one color. When it loses its H plus, it's a different color. That's really just how indicators work. So in acids and acid solutions, they have the H plus on them because there's lots of H plus around to attach to them. And so you're going to see the acid color of the indicator. In a base, OH minus is going to take the H plus off of the indicator, and you're going to see the base color. So to illustrate this, why do they change it different colors? Well, they have different Kas. Bromthiamyl blue, for instance, is Ka 10 to the minus 7. The yellow color is when it's the acid form of bromthiamyl blue. Bromthiamyl blue is yellow in acid and blue in base. So if we put bromthiamyl blue in an acid, it's going to be yellow. Now, what pH will we begin to see it starting to change to blue? In other words, when will it start to see a little greenish color to the yellow? Well, Ka for bromthiamyl blue is 1 times 10 minus 7, which is H plus times In minus over HIN. So let's say that, just assume here, that we start to see the yellow change to greenish color and begin to get a little bit of a bluish hue when the base form of the indicator, the conjugate base, IN minus, is 1/10 of the HIN value. When we get a 1 to 10 ratio of indicator. So that would mean, according to the math, if our yellow form is in acid and our blue form is in base, and green means we're sort of starting to change color, and green happens when the yellow is 10 parts and the blue is 1 part. We can start to see some green at 1 to 10 ratio. Then we need a 1 IN minus and a 10 for the HIN, a 1 to 10 ratio, which means our H plus is going to be 1 times 10 minus 6, or the pH is going to be 6. So in fact, for an indicator with a Ka of 10 to the minus 7, it means that at pH 7, you're going to have half of the base form and half of the acid form of the indicator. In other words, you're going to see the middle color at 7. You're going to start to see some of the middle color maybe at a pH 1 unit below that, and you're going to be finished, and you're going to be all, in case of bromothiol blue, all blue by pH of 8. So the general rule is, whatever your Ka is for your indicator, take the negative log of that. That is the center pH where you're going to have half and half of the two colors. So in other words, you'll be perfectly green at 7. You'll start to see a little green at 6, but you'll be pretty much all blue by 8 because the Ka is 10 to the minus 7. So if you're looking for an indicator that changes color at 7, or in and around 7, and starts to change about 6 and finishes changing by 8, bromothiol blue is your guy. Methyl red is yellow in base and red in an acid, but methyl red changes color around 4, I believe. We'll see a chart here at the end of the notes. So if you've got a strong acid, strong base, because of that strong vertical region, anything that changes color between 5 and 9 would work, because you would catch that vertical region and you'd stop at the right volume. But for a titration of a weak acid and strong base, because your vertical region is much shorter and above 7, you want to make sure you choose an indicator that changes color above 7. So we wouldn't choose bromothiol blue. You'd choose something like phenolphthalein because its change in color is about 8 or 9. So choosing your indicator is important because of the different pHs that things change at. So here is your common indicators and their pH color change. And so just to pick a couple out here, we talked about methyl red. Looking at the methyl red, it changes color at about 5. It starts changing color a little above 4, finishes changing color at about 6 point something. So you see how everything has about a 1 or about a 2 pH unit range here. Bromothiol blue, seeing it, see how it's centered at 7. It's yellow at 6, it's blue at 8, it's greenish in between 6 and 8. Phenolphthalein changes color right around 9. You only start to see the faint pink at a little bit above 8, and it's pretty much dark red by pH of 10. So phenolphthalein actually works well with a weak acid. Okay, so I'm going to wrap it up there and try to get this posted here sometime this morning. So thank you all for your patience and for working through these. And any of these notes that you want to listen to in more detail, you can just watch this again, slow it down, speed it up, whatever. But this would be probably helpful for you for the last 2/3 of chapter 14. Thank you, everybody, for your attention.